Hello everyone and welcome back. So we're starting with the remainder of this video. So this is linked to what's called the DC motor, Fleming's left hand rule and all of that. So let's start. So similarly, a current carrying conductor placed in a magnetic field would also experience a force. So it's a basic idea that we've also used in the last video. The direction of this force can be found using Fleming's left hand rule. And what each of these fingers specifies is shown here. So the thumb is motion. So if you think about this in terms of the letters, so capital M, that's motion. First finger, so F is field. Second finger, C is current. So that's what each of these fingers stand for. Now, for example, if you look at the three fingers of your hand positioned like this, or for example, if you look at a corner of your room, that's exactly what these are, which is that all of these fingers are mutually perpendicular to one another. Now, what these mean is each of these angles is 90 degrees. So for example, this angle between the force and the field, this is also 90 degrees. The angle between the field and the current, this is also 90 degrees. And the angle between your force and the current is also 90 degrees. So they're all perpendicular to one another. All right. Okay. Now we can see this happening in this case of a current carrying conductor placed in a field. So this is the field of the magnet on its own. So that's going north to south. This is how the current is going in the case of the conductor. And I can also figure out the direction of the field of the conductor using the right hand grip rule, right? So for example, if I let my thumb of my right hand point in the direction of the current, I can see that the fingers are curling like this. So this is also clockwise if I look at it like this. So this is how my fingers are curling in this case. So that's like this, for example, down here, and then this and this and this, right? Now what's going to happen here? If I look at it from this perspective, okay, so let's also mark the field lines here. So in this case, it's like this, because this is, okay, I may have made a mistake here. Just double check. Okay, no, it's all fine. So yeah, current is into the page. So yeah, into the page. So this is how my field lines curl. So it's like this and this, this and this. Now what I can see happening here is that in some places the field lines are actually getting added up, but in other places they are cancelling out. So if I want to make the resultant field line in this case, let's say if this is my conductor, so I can see that in the top part, the field lines are getting added up, and that obviously would cause a greater magnetic field strength, so a decrease in spacing. So this is what this looks like. Let me just copy paste some of these to save time. So the spacing has decreased. Right, so more or less this is what it would look like. But in the bottom half, okay, and there's another line here that you can also potentially add, because it's not a linear, it's not a straight field of the wire. So sometimes in books or something, you might also see a field line like this to show the increase in the decrease in spacing, to show the increased magnetic field strength. But on the bottom here, because these field lines are cancelling out, so you rarely have any field lines here. So it looks probably like this. Now in this case, to imagine how the force on this would be, okay, I should have made one more here. Let's try this. So let's make another one like this. So you can imagine these field lines as elastic rubber bands, and when these are going to be released, it's going to move this conductor in that direction. So obviously if these are stretched, if I let go of these, then this force would act downwards. That's one way to understand this, and this is the only time we're talking about this. Other times I'll just use Fleming's left-hand rule. So for example, if I look at this diagram here, so what you should start with, irrespective of whether it's the left-hand rule or the right-hand rule, is always the direction of the field. Because if you do this, then things get really easy. So first thing that I see is that my field is pointing north to south, which is left to right. Right? Now, if this is fixed, then I know that my finger cannot move like this. It can either move like this or it can move like this. So this or this. Now, if it is pointing like this, next thing I need to see is the direction of the current. So current, my second finger is actually into the page. So you can see my thumb points down. So that's how we use Fleming's left-hand rule. So as we just saw with this visualization, this force that I'm getting from the Fleming's left-hand rule, that's also downwards. So that's the idea here. So the following factors affect the force. This is important. So the current flowing in the conductor, so in your wire, in the conductor, the magnetic field strength it's placed in, so basically of the poles, and the third one is the length of the conductor in the field. Right, so all of these, if you increase any of these, that would also cause the force acting on the conductors to increase. Next, reversing the poles or the direction of the current also reverses the force. This is also really easy to understand, because if I talk about this, so in this case, my left hand was positioning like this, right? Now let's say if my, my field is reversed, right? So instead of north to south, let's say if this is north, this is south. Sorry, if this is north, this is south. So my first motion would be to figure out the direction of the field, which is like this, and my finger would point outwards like this. So in this case, the force is up, right? So you just saw that how reversing the direction of the poles actually reverses the direction of the force. Similarly, if my poles are the same, but this time instead of current into the page, if I have current out of the page. So again, this is how it is. And this time my finger would point out towards me. So you might not see my hand when I position it like this. So you can see that the force is upwards. Again, it has been reversed. But obviously, if you do both of these changes at once, however, both changes at once, and you can also try this out. So if I also reverse the field, so it's like this, and if I also reverse the current, so if current is like this, so you can see again, if I've done both changes at once, so my thumb keeps pointing downwards. So I've actually had no changes here. So both changes at once have no effect. This is something important. The examiner does ask this a lot in MCQs. So that's another part of electromagnetism. In the next video, we'll be discussing other things. So see you there. Okay, so that was not true. We are still looking at this video, and because the next video, it's going to cover like similar concepts, so that's going to be different. Let's look at this right now. This is also asked in the context of the chapter of radioactivity and nuclear physics, which is basically that how are charged particles affected in magnetic fields. So for example, in this case, the field that I see is a field out of the page. Right now, because I have a habit of mixing this up, I'll just write it for myself. So this is out of the page. In one case, I have a proton entering. In another case, I have an electron entering. So what's different? What do you need to keep in mind? Now, because we've already studied the chapter of electricity, we know that conventional current is the flow of positive charge. So if we have a positive charge, for example, a proton entering, then what I would take as my current, my second finger, is just going to be the flow, is just going to be the direction of velocity. But we also know that electron flow is actually opposite to conventional current. So if my electron is actually going in a certain way, my current is going to be opposite to that, and that's what I'll be using for my Fleming's left-hand rule. So remember that the current here is the direction of conventional current, which is the flow of positive charge. So for positive charges, current is in the direction of velocity, but it is opposite for negative charges, since current is the flow of positive charge. So for example, if I have to see this deviation here, so again, let's start with the field. Let's listen to my own advice. So that's out of the page. So my index finger is pointing out towards me. The current, the flow is in the direction of the movement of the proton. So that's like this. So my thumb points downwards like this, right? So I'll just show you this. So this is how it's supposed to deviate in a direction like this. What about for the electron? Now it also obviously makes sense that because the electron has an opposite charge, it should be going the opposite way, but let's also see this with the Fleming's left hand rule. Again, current field is out of the page, so that's like this. And now because my electron is moving towards the right, conventional current is actually opposite, so it's going to be like this. Again, this is how it is. So my second finger is actually pointing the other way, as opposed to how the electron is moving. So in this case, the force is upwards. So that's how the electron would move in this case. But there is also something else here, which is that the electron is going to deviate much more sharply, because even though they both have the same charge, the proton has a much smaller mass, so it's going to experience a much stronger deflection. Okay, so electrons undergo a much sharper deflection since they have a smaller mass. This is now all of the subatomic particles here. So neutrons are in orange. Obviously, neutrons are electrically neutral, so they will not deviate at all. So the neutrons just pass through undeviated. Similarly, when we're talking about types of radiation, in that case, gamma is uncharged, so it passes through undeviated. Now this is, what do you call it, field into the page. So this is into the page. So again, that's what I start with the proton. My finger just points like this, so my thumb points upwards, so the proton goes up, right? So something like this. Again, in keeping with what we just talked about, if you just reverse the direction of the field, so this was out, this is in, so naturally the direction of the deflection changes. Previously the proton was going down, now it's going up. So that's the proton. And then similarly, if you want to, you can, the field is into the page, the electron is moving to the right, so my second finger would actually point the other way. So I can see that my electron deflects down, but again, this would be a much stronger deflection as compared to what the proton shows. So that's going to look like this. All right. So yeah, now this is actually all for this video. And in the next one, we'll be talking about more advanced concepts such as the DC motor and whatnot. So see you there.